No doubt in grade school you discussed the three most common states of matter. There's the solid, which has a definite shape, like this pen. There's a liquid, which has a definite volume but not shape, like this water. And there are gases, which have neither definite volume nor shape, like the gas in this balloon. Today we're going to talk about gases, and as a matter of fact we'll be using balloons quite a bit. Now gases still have volume, and they still take up space, but the amount of space that they take up is variable. In fact, they always use up all the space that's available. And one way to look at this is that they are space hogs. One important property of gases is pressure. Pressure is defined as force per unit area that the gas exerts on its surroundings. Now let's see how this idea of gases being space hogs relates to pressure. Gases, like other substances, are composed of atoms or molecules. A gas like helium is composed of individual atoms. A gas like oxygen is composed of O2 molecules. So that I don't have to keep saying atoms or molecules over and over again and driving you crazy in the process, I'm just going to say molecules. And you please remember that sometimes, to be proper, I really mean atoms. Now here's how we picture gases. A lot of molecules bouncing around, bouncing off each other and off the walls of the container. Take our balloon here, for example. Inside, we have trillions of molecules bouncing around at high speed, like popcorn popping in a microwave popcorn bag. The combined bouncing of so many molecules exerts a push on anything they contact, and we call that push pressure. The molecules in the balloon exert a pressure outwards on the walls of the balloon, pushing the balloon out into a spherical shape. Now consider this question. If the molecules in the balloon keep pushing outwards, why doesn't the balloon continue to expand indefinitely? Well, to answer this question, think about what's going on outside the balloon. The balloon will continue to expand only until the pressure of air molecules outside the balloon pushing in exactly balances the pressure of the molecules inside the balloon pushing out. We have a fancy name for this kind of balance in chemistry. We call it equilibrium. When the pressure of the gas inside pushing out equals the pressure of the gas outside pushing in, we say that equilibrium is achieved. Now, to be quite honest, there is one more force pushing in on the contents of the balloon. That is the elastic force of the balloon wall itself. So, strictly speaking, the pressure of the gas inside the balloon is balanced by the sum of the inward push of the elasticity of the balloon wall plus the air pressure outside the balloon. Okay, just to drive this point home, watch this. Here's a balloon in a jar. Clearly it's at equilibrium. The gas pressure on the inside pushing out is balancing the gas pressure on the outside and the pressure from the plastic material in the wall pushing in, so the balloon just sits there. Now we're going to pump the air out of the jar. Well, that's an interesting way to blow up a balloon, isn't it? Why did the balloon blow up? Well, think of our picture of balloon equilibrium. If we remove the air from the outside of the balloon, the inward pressure that that air was exerting and that was balancing the outward pressure of the interior gas is now gone. So the balloon expands until the outward pressure of the interior gas is balanced by the inward push provided by the plastic in the balloon wall. Of course then, when the jar refilled with air, the balloon contracted back to its original size. The symbol we use for pressure is P. At this point, let's ask ourselves, what factors influence the size of pressure for a given gas? First, let's look at the number of gas molecules in the sample. Without changing anything else, that is, the size of the container or the temperature, those kinds of things, what ought to happen if I increase the number of molecules in my gas sample? Well, if the pressure results from collisions of gas molecules, and there are more molecules, there ought to be more collisions and thus more pressure, right? One way to visualize this is to think of a bunch of pigs in a puddle, surrounded by a fence. The pigs want to be as far from each other as possible to stay cool. If you keep adding more pigs to the puddle, there's less room for each to move around. Each pig bumps into the other pigs and the fence more often, and this results in greater pressure on the fence. Now, by the same token, when I add more molecules to my gas, then more molecules are crammed into the same space, they bounce into one another and into the walls more often, and the pressure increases. Now let's talk about how we measure pressure. One way of measuring pressure is to use an instrument called a barometer. The oldest kind of barometer uses a long, closed tube containing mercury. This tube has a vacuum at the top, and the bottom opens into a bowl of mercury, which is open to the air. The higher the air pressure surrounding the barometer, the higher the mercury is pushed up the tube by the air molecules. This barometer provides one of the units for measuring pressure, millimeters of mercury. The pressure is literally given by the height of the mercury up the tube in millimeters. Now, this kind of barometer was invented by a friend of Galileo's named Torricelli in the 1600s. So, the millimeter of mercury unit is also sometimes called the torr. While we're at it, why don't we talk about other units for describing pressure? Aside from the torr, the one most commonly used by chemists is the atmosphere. 1 atmosphere is the pressure of air at sea level, and is equal to 760 millimeters of mercury. One unit you might be familiar with is the psi, or pound per square inch. And another unit is the Pascal, abbreviated PA. I'm going to take the easy way out and suggest you read more about these units in your textbook.